Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The purpose of this lecture is to talk about kernels of linear transformations and some of their properties. To properly understand this lecture, you need to know something about functions, what linear transformations are, and that's it. And those were subjects of earlier videos. So let's get started. So let me remind you what a linear transformation is quickly. So a linear transformation, we have two vector spaces. The setup is that we have a vector space V as our domain and W as our codomain. And then we have a function, a map from V to W, T, for example, here. And then this map may or may not be a linear transformation. It is a linear transformation if it satisfies two properties. The first property is that T of x plus y is T of x plus T of y, regardless of which vectors x and y in V you choose. So for example, so that means geometrically that if you have x here, it goes somewhere. It goes to T of x. X is some element of the domain and T is a map. So you have to be able to plug in every element in the domain and you get something T of x in the codomain. Now, y is also an element of the domain and you can send that somewhere, T of y. Those are all, any function would do that, would send elements of the domain to the codomain. But because V is a vector space, we have an addition. So x and y are there in V. We have an irresistible urge to add them. So if you add them, you get something else, x plus y. And the question is that, do you have a choice of where to send x plus y? If it's a linear transformation, you don't. If you have sent x to T of x and y to T of y, then x plus y should go to T of x plus T of y. Now, x plus y really goes to T of x plus y. So T of x plus y, where x plus y goes, needs to be T of x plus T of y. In addition, so this is called preserving the addition. But it also has to be true that T of alpha x is alpha T of x. So wherever x goes, if you multiply x by a scalar, you get something else in V, and then you don't have a choice where that goes. That needs to go to alpha times T of x. So that's what a linear transformation is. And linear transformations are, after the definition of a vector space, probably the most important notion in linear algebra. Okay, in a previous lecture, we talked about the image of a linear transformation. And let me remind you of what we did, not because we need it for this lecture, but just because it gives us a blueprint for what we might want to do going forward. So again, we have two vector spaces and we have a linear transformation from one to the other. And then T of V, or the image of T, what I will call the image of T, is all the elements in the codomain that are hit by some element. That for them, there's some element V in V, so that T of V is W. So if you take your codomain is the target set, is the canvas on which you're throwing elements of V at. Not every element is hit. Those elements of W that are hit, those elements, that subset of W, is called the image or the range of T. Now, we proved certain things about the image, is that in the case where we have V and W vector spaces and T is a linear transformation, the image is a subspace. You can define image for any function, but for linear transformations, it tends to be, it has to be a subspace, and therefore it has a dimension. The dimension of the image, we call the rank of the linear transformation. And it's obvious from the definition that the map is onto, meaning that everything is hit if everything is hit, if the image is W. So, image is something that tells us about onto-ness, among other things. We also proved that if you have a basis for the vector space, and then you send those basis elements over, you get a spanning set for the image. So the image is the span of those guys. So one of the things that we said is that given the image, we know that the function is onto or not. If the image is everything, the function is onto. But it tells you a little bit more than whether or not the function is onto. For example, if the function is not onto, it tells you how far away are you from being onto. So that's sort of a good thing. And we want to, our purpose in this lecture is to see, is there an analogous subspace for one-to-oneness? Is there subspace that tells us about one-to-oneness, or how close or how far we are from being one-to-ones? And the answer is yes, and that's what we will be talking about next. Okay, so I'm going to define this kernel which is a very important concept in linear algebra. So so what's the setup? What do I have to have before I can start talking about a kernel? You have to have two vector spaces, V and W. For first-time viewers, V and W could be R5 and R7, for example. And T is a linear transformation from V to W. Then the kernel of T is very simply defined, is all the elements in the domain that are mapped to the zero vector of W. And one might wonder, why would you privilege the zero of W and care about it that much to give a name to all the elements that go to it? But we do, and that will become clear in the course of this lecture. So this thing is called the kernel or the null space of T. And you might wonder, why would you use the word null space, which we've already used for matrices in the context of linear transformations? And there is a reason for that. That will become clear a little bit later in this lecture, but in a different lecture, I will expand on that connection between matrices and linear transformations. In fact, that will be the subject of a whole bunch of lectures. Okay, so again, if you want to just look at it pictorially, we have a domain, we have a codomain, we have a linear transformation, and the kernel is the stuff in the domain that end up at the zero vector of W. So the image is in the codomain, the kernel is in the domain. The kernel is all the stuff that goes into zero of W. And you might notice that zero of V is in the kernel, because one of the properties of linear transformations, which we proved in the first lecture on linear transformations, is that it must take the zero of V to zero of W. Every linear transformation takes the 0 to 0. So 0 of V is definitely going to go to 0 of W, but the kernel is everything else, also includes everything that goes to the 0 of W. Okay, now the first thing that we want to prove about the kernels is that if, again, the setup is that we have two vector spaces and we have a linear transformation, and the first thing we want to prove is that the kernel is a subspace of V. This is important for us in linear algebra because we don't really like thinking about just subsets of elements. I mean, if you have a bunch of elements together and they don't form a subspace, linear algebra has a hard time talking about them. But if they're a subspace, then we can talk about their dimension. We know they're closed under the linear combinations. There's lots of things we know about them. We can find a basis for them and so forth. And kernels are always a subspace. The stuff that goes to 0 is always a subspace. Okay, and we will prove that in just a second. But because it's a subspace, we can give a name to its dimension. So again, the same setup. The dimension of the kernel of a linear transformation is called the nullity of that linear transformation. Again, there's a connection with matrices that we will explore later. Okay, so how am I going to prove that the kernel is a subspace? Well, how do you prove anything is a subspace? Well, one way to prove that something is a subspace is to show that, I mean, the kernel is already sitting in this bigger vector space V. V was the domain, and I need to show that it's a subspace. How do I do that? All I need to do is to show that the zero vector of V is in kernel. I have to show that it's closed under addition. If I take two elements in the kernel, add them, I get something in the kernel, and it's closed under scalar multiplication. If I take an element of the kernel and multiply it by a scalar, I get something in the kernel. Scalars for first-time viewers are always real numbers. For second-time viewers, they could be complex numbers, rational numbers, or a finite field, ZP. For third-time reviewers, they can be any general field. Okay. So to get started, we have to show that the 0 of the vector space V is actually an element of the kernel. And that follows from the fact that I alluded to earlier, that if you take T and apply it to the 0 of V, you will get 0 of W. Why? Because that's what linear transformations always do. It wasn't a part of the definition, but that was something that we proved. The proof is not that hard. You might want to think about how you prove that, but T, 0 of V goes to 0 of W. We have proved that in a previous lecture. Okay, now I have to prove to you that the kernel is closed under addition. So I take two elements, V1 and V2 in the kernel. So I walk into the kernel, look around, take two arbitrary elements, V1 and V2. And now I've got to convince you that even though because V1 and V2 are in the kernel, there's some V1 plus V2 is also in the kernel. V1 plus V2 is somewhere in V because V is a vector space and it's closed under addition. But why is V1 plus V2 in the kernel? Well, how do you show that something is in the kernel? So you're sitting in a vector space and a vector element walks through the door and says, I'm in the kernel. Well, how do you check? Well, what is the kernel? The kernel is all the elements that go to the zero. Go to zero how? By applying T. So to see if something is in the kernel, you apply T to it and see if you get zero or not. So check if it goes to zero. So we have to find T of V1 plus V2. And if it ends up being the zero of W, then we know V1 plus V2 is in the kernel. But what's T of V1 plus V2? Here's where we use the fact that T is a linear transformation. You might want to stop the video right now and complete the proof yourself. You should do that almost at every step of every one of these videos. So T of V1 plus V2, T is a linear transformation. So one of its defining properties is that I can split it up, T of V1 plus V2 to T of V1 plus T of V2. But what's T of V1? Well, V1 is in the kernel. So T of V1 is the zero of W. And T of V2 also is the zero of W because V2 is in the kernel. And 0 plus 0 is 0. So V1 plus V2 goes to the zero of W. So V1 plus V2 is in the kernel. And I just showed you that the kernel is closed under addition. I took two arbitrary elements, showed that their sum is in the kernel. Okay, then we have to do the same thing for scalar multiplication. Pick an arbitrary element in the kernel, an arbitrary scalar, and multiply them. You get something in the domain because the domain is a vector space, but is it in the kernel? How do you know if something is in the kernel? You apply T to it, see if it ends up at zero of W or not. So T of alpha V, what is that? By defining, again, because T is a linear transformation, the whole thing only works for linear transformations. You could define the kernel for any function from a vector space to another, but it won't be a subspace if it's not a linear transformation. So T of alpha V is alpha T of V, or at least it won't necessarily be a subspace if T is not a linear transformation. And T of V is 0 of W, and alpha times 0 of W, we've proved in any vector space is 0 W. And so we showed that alpha V is in the kernel also. Why? Because it went to 0. And so that means that it's closed under scalar multiplication also. It has the 0 vector closed under addition, closed under scalar multiplication. So it's a subspace, and we're done with the proof. Okay, now let's look at an example. So we have a map from R3 to R2, R3 three-dimensional space. That's a vector space. R2, the plane, that's a vector space. And this map takes alpha, beta, gamma, which is a point in R3, and sends it to the point alpha minus 2 beta, beta plus gamma. And we're asking, what is the kernel of this linear transformation? But before we can answer that, we have to make sure that we know that it is a linear transformation. You can prove that directly by showing that T of x plus y is T of x plus T of y, where x and y are elements of R3 here. And also T of alpha x is alpha T of x. Again, alpha is an arbitrary scalar and x is an element of R3. Or you could note that this is a matrix transformation. What's a matrix transformation? We have said this in the earlier lecture on linear transformations, the first lecture on linear transformations, that when a matrix walks through the door, you can think of it as a linear transformation. So here the matrix A that has 2 rows and 3 columns has walked through the door. And because it's a 2 by 3 matrix, it gives you a linear transformation from R3 to R2. How? Well, if you take anything in R3, how do you send it to R2? You multiply it by this matrix. A times a column vector a column vector with 3 entries is going to be a column vector with 2 entries, something in R2. And if you take alpha plus alpha beta gamma and take A times alpha beta gamma, you will get alpha minus 2 beta, beta plus gamma from what this matrix is. So this linear transformation is a linear transformation that you can think of it as having come from this matrix. And matrix transformations are always linear transformations. We proved that. And therefore, this is one way of saying this is a linear transformation without having to do any calculations. Okay, so we want the kernel. What are those? Those are the elements of R3 that go to 0, that are sent to 0. How are they sent? They're sent to 0 via T. So if I apply T to them, I get 0. So I want alpha, beta, gamma, those elements of R3, the T of them is 0, 0. It's the 0 of W, the 0 of the target set. vector space. And so that means that T of alpha, beta, gamma is alpha minus 2 beta, beta plus gamma. So I want that. And therefore, that means that I need to find which alpha, beta, and gamma are that. Another way of thinking about it is that I want those elements alpha, beta, gamma such that A times them is 0, 0, because A times alpha, beta, gamma is alpha minus 2 beta, beta plus gamma. In other words, I want the null space of A. So the kernel of T is the null space of A, which is the reason of which we will talk to about later in more detail, why the kernel of a linear transformation is also called the null space of the linear transformation, because when you are talking about a matrix transformation, the kernel is the null space. The kernel is another name for null space. And you might say, well, okay, matrix transformations are just one example of linear transformations. There's plenty of others. And spoiler alert, for finite dimensional vector spaces, there aren't any others. And that will be the subject of a few lectures down the line. Okay. And how do you find the null space? Well, you find the reduced row echelon form of A and solve the system, which I will do next. So we're same problem. And we have this matrix A, and we want to find its null space because that's the kernel of the linear transformation T. And again, so to repeat that, to say that x goes to 0, T of x is 0, is the same as saying LA of x is 0 or A times x is 0. Those are all the same statements. One is about linear transformations, one is about matrices, but they're the same statements. They're all asking what happens when you apply T to x or multiply A by x, and those are the same thing. And kernel of T, if you solve it, finding doing it reduced row echelon form and solving things is not something you want to do in public. You should do it in privacy of your home. If I have not made a mistake, then the kernel is these elements. The null space of that matrix is all the elements in R3 of that are of the form minus 2R minus RR. And we know it's a subspace, so we can also write down a basis for it. Minus 2 minus 1, 1 is the basis for it. And this also says that the nullity of T, which was the dimension of the kernel, is 1. Among other things, this says that the map is not 1-to-1. Why? Because a whole bunch of things went to 0. 1-to-1 map is a map where no two things go to the same place. Here, I mean, let's not worry about anything else. We have this whole one-dimensional subspace that's going into the 0 vector of W. And one-dimensional space of R3, what is that? That's a line through the origin. So this is a line through the origin, and all the points in that line are going to the 0 vector. Okay. All right. Now I want to tell you a theorem that at the beginning you might say this has no content, and so let me explain the no content part of it. So the setup, same as usual. We have two vector spaces, and I've got a linear transformation T from one to the other. Then the first thing I'm going to say, which is something that I've talked about in the previous lecture about images, is that T is onto if and only if the image is W. Well, this is obvious. This is actually the definition of onto. The function is onto, meaning that every element in the image is hit if every element in the image is hit, which would mean that the image is the whole W. Okay, so there's nothing there to prove there. Here's another obvious fact. If T is 1-to-1, the kernel is just the 0 vector. Why? Well, 1-to-1 means no two distinct elements go to the same place. We know already that 0v goes to 0 of W, and if the map is 1-to-1, no one else has the right to go to 0 because the map would not be 1-to-1 if it did. So the only thing that can go to 0 of W is 0 of V, and therefore the kernel is 0 of V. So nothing of interest. And why did I put this up? And the reason is that, somewhat surprisingly, the converse of this is true. This is what makes kernels important. That if the kernel is 0, then T is 1-to-1. Now, this is not obvious at all. If the kernel is 0, that means that all you know is that the only thing that hits the 0 of W is 0 of V. But what does that mean that T is 1-to-1? Why couldn't it be that two other elements somewhere else don't go to the same place? Not the 0 vector, not only the 0v goes to 0v, but why is it that no two other vectors go to the same place somewhere else? They don't. And then that needs a proof, which will be what we have to do. So from that theorem, the only content part But an interesting one is this one, that if the kernel is 0V, then T is 1 to 1. That's, again, not obvious. Stop the video, think about why that's not obvious, or try to prove it if you think it is obvious. If 0 is the only element that goes to the 0, why isn't it not that two other elements don't go to the same place somewhere else? How do we know that two other elements don't get mapped to the same place? Well, how are we going to prove that? I mean, the theorem says that they don't. How am I going to know if that's true or not? Well, I'm going to start by saying, well, let's say pick two elements that did go to the same place. So assume that the kernel of T is the 0 of V. The kernel is just the 0 vector, nothing else. I'm not saying that the 0 is in the kernel. That's an obvious fact. That's always true. I'm saying the kernel is the 0 vector. That means there's nothing else in the kernel. And I assume also that V1 and V2 were two elements of V, and they went to the same place. Now, if you assume that V1 and V2 are two different elements of V, then you would want to get a contradiction. But if you don't assume that, and I'm not assuming that, then what you want to do is you want to prove that V1 and V2 were the same after all. You want to prove that V1 equals V2. So that's what I want to do. I want to show that V1 equals V2 if they went to the same place, and if the kernel was the 0 vector of V, and T is a linear transformation, then V1 equals V2. So how am I going to show that? Well, what do I know? I know that T of V1 equals T of V2. Well, bring them to one side. Subtract T of V2. This is all happening in the codomain in W. So T of V1 minus T of V2 will be the 0 of W. Okay, so what? But I have a linear transformation, and I have a resistible urge to combine T of V1 minus T of V2 into T of V1 minus V2. T of V1 minus V2 is T of V1 minus T of V2. So T of V1 minus V2 should be the 0 of W, and that's because T is linear. But now look at this V1 minus V2. Think of that as an apple. T of apple is 0. T of V1 minus V2 is 0. What does that mean? That doesn't mean V1 minus V2 is 0 right away, but it does mean that it's in the kernel because it went to the 0. Anything that goes to the 0 is in the kernel. But the kernel here is just the 0 vector, so V1 minus V2 must be 0. And if V1 minus V2 is the 0 of V, then V1 equals V2, and we are done. We showed that if two elements go to the same place, they are the same. And the proof is complete. And T is 1 to 1. Again, if you know that the kernel is the 0, then you know the T is 1 to 1. So this gives us a really nice way of looking for when a linear transformation, but only linear transformations, are 1 to 1. You check the kernel. Is the kernel just the 0 vector? Instead of worrying about the whole vector space, you just worry about the stuff that goes to the 0 vector. Okay, so kernel of a linear transformation is important since it tells you more than what just goes to 0. It tells you more, and I'm repeating myself. If the kernel is just the 0 vector, then no two other elements are allowed to be mapped to the same place. This only works for a linear transformation. I want to emphasize that. And I've said this in the previous lecture on images, that in mathematics, whenever we have a binary question, a question whose answer is a binary answer, yes or no, we try to change the question. We think of that as not a great question, and to a question that gives us a spectrums of answers. And we saw an example of that in the previous lecture. Instead of asking if a linear transformation is onto or not, you ask, what's this image? If the image is everything, you know it's onto, but if it's not, you don't just get a no for an answer. What you get is that how far you are from being onto, or how close you are to being onto. And now we know that we have a similar way of doing things for one-to-oneness. Instead of asking, is this linear transformation 1 to 1 or not, we ask, what is the kernel? Why? Because if the kernel is just the 0 vector, we know the function is 1 to 1. But if the kernel is not 0, we have more information. We have something about how far we are from being 1 to 1. In fact, the kernel works in a much more systematic way that this seems, and I want to pursue that further for my final theorem in this lecture, after which I will give you two applications. I mean, two reformulating things you already maybe know. So again, the setup is V and W are vector spaces, and I have a linear transformation from V to W. And here what I want to do is I want to know, I have some particular elements in W that I like, and I want to know what gets mapped to it. I want to find the pre-images of that element. If that element was the zero vector of W, the pre-image is the kernel, but this might not be the zero vector. So B is in W. That's that guy that I like in W that I want to investigate what goes to it. And assume that I found one thing, A, that does go to it. Well, the reason for that is that it might be that nothing hits it. And it's not fair to ask the linear transformations any questions about the elements of W that it doesn't hit. It doesn't see them. It's taking elements of V and sending them to the image. Anything else, it's blind to those. It can't see those. It doesn't have any information about those. The linear transformation will do that. It could be a huge stuff in W that are unknown to this linear transformation T, and it's not fair for you to ask anything about those elements. So this B is some element that we know something at least hits it, and that thing is A. So we have an element in W that we like, and we know that it hits by something. And then my question is that what are all the other elements, or what are all the elements that go to B? One of them I know A, but what about the rest of them? And this theorem tells me. The theorem tells me that elements of V whose image is B, that's all the elements that go to B, are of this funny format. They're A. What's A? A is that one element that I already knew that goes to B, but A plus K, where K is in the kernel. So you take the elements of the kernel and add them to A, and you get elements that go to B. That part is actually pretty easy to prove. But you don't. There's no other element that goes to goes to B. Every element that goes to B is of this form A plus K. This theorem actually supersedes the previous theorem, the theorem that said that if the kernel is 0, then T is 1 to 1. And I'm actually reproving that. I didn't have to prove that theorem. By proving this, I already have another proof of that fact. But that fact is important enough and straightforward enough, like the proof wasn't that difficult, that I wanted to do it separately and give you a different proof. But this one is also not super difficult, but it will shed new light on how the kernel works. So let me repeat the way I'm thinking about this. So I've got V, I've got W, and T goes from V to W. Actually, as I was saying, T really goes from V to the image of T, because it's not seeing the rest of it. So T is a map from V to image of T. Think of it that way. And then we have the kernel. The kernel is all the stuff that goes to the 0 of W. Okay? What this theorem says is that now, if you want to see what are all the stuff that go to B, so there's a whole box here of things that end up at B. Well, one of them I know what it is. A goes to T of A, and T of A is B. That's what I know. But what this theorem tells me is that everything in that box is A, that little A, plus the kernel. What do I mean by A plus the kernel? I mean, take elements of the kernel and keep adding them to A. You get a whole bunch of elements. That's exactly the elements that go to B. And then there might be other elements, like there might be another element D that goes to something else, T of D. And then again, D plus the kernel of T is all the elements that go to T of D, and this continues. So the domain is split up into these boxes. People call those fibers or cosets, and there's all kinds of names for them, and they play a very important role in slightly more sophisticated mathematics. Watch my videos on abstract algebra, and you'll see how we can develop this into whole theory. But right now, what we want to know is that we've got the kernel, and then we've got these other boxes that we can get from the kernel. And how do we get them? We just could take some element not in the kernel and keep adding them to the elements of the kernel. And all the stuff in the box go to the same place. And each box goes to different ones. I mean, so we can see here that if the kernel now is small, all these boxes are sort of the same size. There's a one-to-one onto correspondence between a one-to-one correspondence between them. If the kernel shrinks, that means this initial box shrinks, and so all the boxes shrink. And so fewer elements go to, if fewer elements go to the 0 of V, fewer elements go to B, fewer elements go to T of D, fewer elements go to and so on. And of course, the previous theorem is true. If the kernel is just the 0 vector, then there's nothing to add to these guys. And the only thing that goes to T of A is A, because the only thing you can add A to according to this theorem, is the zero of the kernel. Okay, but before we get too excited about this, or at least I get excited about this, I should prove the theorem to you. Why is it true? So we want to prove that we know that T of A is B, A goes to B, but I want to show you that if I look at the set whose consists of all the elements that go to B, that is A plus K. Every element there is of the form A plus K, is this set, A plus K, where K is in the kernel. Now, whenever you have two sets that you want to show that they're the same, you have to show two inclusions. One set is included in the other is included in that. So let's start. So the first thing I'm going to do is to show you that the second set, the A plus K guys, actually are in the left-hand side set. So every element of the form A plus K does go to B. So let C be A plus K. A was that one element that I knew already went to B, and K is some arbitrary element of the kernel. C is A plus K, and I want to show you that C also goes to B, the same place A went. And how do I show that? Well, C is claiming I'm going to B and I don't believe it. What do? Well, apply T to it, see if it goes to B or not. So we want to show that the image of C is B, and all we do is find T of C. Well, T of C is T of A plus K because C is A plus K. What's T of A plus K? Well, T is a linear transformation, so I can split that up. We use that fact all the time. All of these things are only true for linear transformations. So T of A plus K is T of A plus T of K. So what? Well, what's T of K? K is in the kernel. Where does it go? What's T of K? It's the zero of W. So I get T of A plus zero of W, I get T of A. But what was T of A? T of A is B. And I'm done. And so T of C is the same as T of A, and T of A was B, so C goes to B as I wanted to. So I just showed you that every element on the right-hand side set, A plus K such that K is in the kernel, is an element of the left-hand side. What is that? All the elements of V whose image is B. Now I've got to do the other one, which takes a little bit more work or a little bit more thought, which is if I have something that goes to B, why does it have to be of this form? So let's pick something that's C in the domain that we saw that it goes to B, and we want to show that it's in that box. It's of the form A plus K. So what I need to show is that C is A, our original A, the original guy that went to B, plus an element of the kernel. That's what we have to do. So what I'm going to do is that I'm going to let, I have A and C. A was that original element that went to B. C is this other element that goes to B. And I want to know that C is A plus something in the kernel. So I have A and C. What I'm going to do is I'm going to let K be their difference, C minus A. I'm in a vector space. I can add, I can subtract, and it's a free country. I can subtract. So I'm letting K be C minus A. Now, if K is C minus A, then C is A plus K. So you might think, well, so then am I done? Because I wrote C as A plus K, and that's what I wanted to do. I'm not quite done yet because K, I don't know what K is. I need to show you that K is in the kernel. But if I show you that K is in the kernel, then I'm done because I wrote C as a sum of two things, one A and the other K, which is an element of the kernel, and that's what I wanted to show. So all that remains to show is that K is in the kernel. Okay, well, you're sitting there, an element K has walked through the door claiming to be in the kernel. How do you check that? Proof of the pudding is in the eating. Apply T to it, see if you get 0 or not. So, so we look at T of K, but what is K? C minus A. So T of C minus A. And again, by now you know what to do. T is a linear transformation. You split this guy up and you say it's T of C minus T of A. So what? Oh, but what was T of C? It was B. What was T of A? That was B. And so it's B minus B and it's 0 and we're done because now K is in the kernel. And I showed you that C is A plus something in the kernel. Okay. So again, this theorem tells you that the kernel is sort of a control center. It's telling you what's happening in all of V, not just the stuff that goes to 0, but it's controlling what's happening everywhere else. It has an effect that permeates the whole domain. And so that's why it's important. Okay, now what I want to do is I want to show you two applications. And these are not really, I'm not going to solve anything for you. I'm going to really recast some ways of thinking about things in some other way and show you how this theorem about fibers, this theorem that told you what are all the elements that get mapped to one element, can be used in some, or it can be thought of and useful in some ways. So let's say you've got a 5x4 matrix and you have a 5x1 column vector B. A is your matrix, B is your column vector, and you want to solve AX equals B. This is a system of 5 equations and 4 unknowns, and you want to solve it. You want to, and you know how to solve it. We use Gauss-Jordan elimination, or what I think is more appropriately should be called the method from the 9 chapters, because it was done a long time before Gauss and Jordan were thought about it in China. So one to solve AX equals B, a 5x4 matrix, 5 equations and 4 unknowns. And you know how to do that. But that's not my point here. I want to show you a connection with the previous theorem. And I'm going to translate this to make it more complicated. So I'm going to say, well, look at A is a matrix, but as a matrix, it gives us this linear transformation LA from R4 to R5. How is that defined? Well, LA of X is AX. What's X? X is some element. What's X? Is an element of R4. And when you take A and multiply it by X, you get an element of R5, because A is 5x4, X is 4x1, and so the result will be 5x1. So LA sends elements of R4 to R5. Okay, it does do that. So, so what? Now, solving AX equals B is the same as, if you want to solve AX equals B, that's the same as saying you want AX to be B, but AX is LA of X. So you want LA of X to be B. So if you think of it this way now, what you're asking is that what are the elements of R4 that get mapped to B? That was exactly the question we asked before. What are the elements of the domain that get mapped to this one particular element? So again, I'm not trying to solve the problem. I'm trying to get you to think about a familiar problem, solving systems of equation, in a slightly different way. Now we're thinking of, I've got a codomain. I'm using the imagery of functions. I have a codomain. I have an element in the codomain, and I'm asking, what are the elements that go to it? What is the pre-image of that element? That's one way we can now talk about it. And I'm just repeating myself on the slide, that solving AX equals B is the same as finding pre-images of B for the linear transformation in LA. And the theorem says, to do that, you find one pre-image, that A, that one element that hits it, and then you add to it the elements of the kernel. Okay. Now, what's the kernel? The kernel is the null space. We talked about this before, but the kernel is all the V in R4 that LA sends to 0. And so that's V in R4 such that AV is 0. That 0 is the column vector 0, and that's the null space of A. So, and another way of thinking about it is that the null space is the solutions to the homogeneous system, AX equals 0. We were trying to solve AX equals B, but now we see that solving the homogeneous one has some advantages. And then so it gives us a roadmap, and it says, find all the solutions to X equals 0, solve the homogeneous system and find all of the solutions, find the null space, and then find one solution to AX equals B, and you add that one solution, that one particular solution to that general solution of AX equals 0, and you get all solutions to AX equals B. And this also gives us other ways of thinking about this. Remember, solutions to X equals 0, the null space is a vector space, is a subspace. But now what this says is that solutions to X equals B, they're not subspaces necessarily, unless B is 0. If B is not 0, they're not. But what they are, they're translates of subspaces. So you take this subspace, which is the solutions to X equals 0, and you translate it. So, for example, the solutions to this 5 equations, 4 unknown things, the solutions to X equals 0 might be 2-dimensional. That means that it's a plane in R4. It's a plane through the origin in R4. That's the null space. Some plane through the origin, maybe, if it's 2-dimensional. And then what this says is that to get solutions to any AX equals B, what you have to do is to take those elements in that plane and just add one element to them. So one vector, so shift them all up one. So it's a plane again, but not through the origin. A plane not through the origin is not a subspace, but that's what the solutions to x equals going to be, x equals b going to be, either the shifted lines through the origins, planes through the origin, three-dimensional spaces through the origin, and so on, shifted ones. So this helps us sort of think about what solutions to a system might look like in higher dimensional spaces. Okay, my final application, and then I'll stop the lecture, is about differential equations. I'm not going to solve a differential equation, but I'm going to show you that the same thought process that went to solving systems of linear, thinking about systems of linear equations in terms of pre-images of elements can work for differential equations, which is why if you want to take a honest linear algebra, differential equations class, you should already know linear algebra. So this is a differential equation, y double prime minus 2 sine of x y prime plus ex y equals cosine of x. It's an equation because of an equal sign, and we're looking for something. What are we looking for? We're looking for a function, not a number, but a function y. And it's a differential equation because the function involves double derivative and a first derivative, second derivative and a first derivative. So I'm looking for a function y that if I take its second derivative, then take its first derivative and multiply that first derivative by minus 2 sine x, and take the function multiplied by e to the x and add all of those up, I get cosine of x. That's what I'm looking for. I'm not going to solve for you this. That would be something that you would do in a differential equations class, but I will take you to sort of the first step about thinking about how to solve this problem. And what we'll do is that first we have to come up with this vector space because we're talking about linear algebra. So V is going to be this vector space of smooth functions from R to R. Smooth functions, all I mean is functions that have as many derivatives as you want. It doesn't have to be that narrow. It could have fewer derivatives for this problem, but might as well assume that V is all the functions from R to R that you can plug in elements in R, and you get elements in R, but that you can take as many derivatives as you want. So, for example, e to the x, cosine x, sine x, x to the fifth. All of those are functions that you can take as many derivatives as you want, and there are smooth functions from R to R. Okay. Now I'm going to define a linear transformation. So what is that? There doesn't seem to be any linear transformation here at all. Well, it's going to be this. It's going to be a linear transformation from V to V. Actually, this is a linear operator. So what is it going to do? It's going to take a function and give you another function. So you feed it a function. What comes out? It comes, you take its second derivative, minus 2 sine x f prime of x, plus e to the x f of x. This is not surprising where I got this. I got that from the differential equation I want to solve. I'm ignoring cosine of x for now. So this function, you feed it functions, comes out another function. So for example, if you feed it e to the 2x, and if you do the calculus part of it, taking the derivatives and so on, you get this more complicated function. So it just seems like it complicates your world. It's going to give you 4 e to the 2x minus 4 sine of x e to the 2x plus e to the 3x. And if you feed it other functions, you'll get other functions. What are we looking for? We're looking to solve the differential equation. So what we want to, this map, by the way, is a linear transformation. That takes proof, which I did, I think, in some other video earlier that I did when I was proving things are subspaces. I proved basically what you need to. I didn't prove this particular fact, but I proved what you needed. But right now, let's just assume that we know that this is a linear transformation. Actually, because this is a linear transformation, this differential equation is called a linear differential equation, even though it has e to the x and sine and cosine and so on in there. But because in terms of y and y prime and y double prime is acting linearly, t is a linear transformation, this is a linear differential equation. Okay, so what are we looking for? We're trying to solve the DE. What does that mean? Well, what that means is that we want to find all the functions that when you apply t to them, you get cosine of x. That's what we want to do. So what are all the functions that go to cosine of x? So we're in the same format as before. We're trying to find the pre-images of cosine. So we have v here and v there. Functions are being sent over, and we want to know which ones hit cosine of x. So we're looking for the pre-image of cosine of x. So our theorem tells us what to do. You first find the kernel and what's the kernel? The kernel, and then you find one solution to 2ff equals cosine of x, one particular function that goes to cosine of x, and then you add them up. And so you get all the solutions to this differential equation by adding one particular solution to the original equation. So you have to, by hook or crook, find one function that when you take its second derivative and then the first derivative multiplied by minus 2 sine of x plus e to the x, you get cosine of x. And in differential equations, you find that solution basically by trial and error. You say, well, maybe it looks like this, you plug it in, see if it works or not. And you give yourself some room by having some undetermined coefficients. And then you try to figure out which combination of those coefficients works. And often, actually, you have to solve a system of equations to find what that is. So, you've in differential equations courses, you learn how to find that one particular solution. And then you have to find the general solution to the homogeneous equation. Homogeneous equation being the one where the right-hand side is 0, and there are methods for doing that. And the advantage of solving those is that the answer is a subspace. And therefore, it has a dimension, and all you have to do is find a basis for it. And if you know, especially if you know what the dimension of that vector is, the subspace is, you are halfway there. And all of those are things you learn in differential equation class, and you do. But what linear algebra does for you is not solve the differential equation, but gives you a roadmap to how to think about it. You have a differential equation. It says, don't think of it that way. Think of it as you have a linear transformation, and you're trying to find the pre-images of one element. And the way to do that is to find the kernel, the stuff that goes to 0. That's solving the system of the homogeneous differential equation. And solve that. That's an easier problem. Solve that, and then do this other thing, which is find one thing that hits the function you want, and then you can find all of them by adding the general equation, the general solution to the homogeneous equation, the kernel, to that one element. This brings us to the end of this discussion of the kernel. I will see you in the next lecture. The next 2 lectures, we will talk about matrix transformations in a little bit more detail, but then we talk about the dimension theorem that will connect the kernel and image of a linear transformation in fascinating ways. See you later.